So this is going to be a true workshop talk. It's about something that we have not published. It's a new idea that we're working on, and I'd like to hear your thoughts about it, and let's see where it goes. So let's start with what the problem is. Let's start thinking first about what kind of problems we might want to solve that we cannot really solve right now. So one example would be personal search, right? So suppose you have your favorite compute device, and it records your life, your interactions with the world, and it can retrieve things on demand when you need them and give you context for any particular situation. Right? This would be a great thing to have. We don't have it. Personal search, as it exists right now, is limited by domain, and even within a limited domain, it doesn't work very well. If you wanted to do this, you could not do this the way you do typical web search, because you can't afford to hire editors to label, oh, this result is good in that context for every individual person. That would be a very ridiculous approach. Instead, you need to be able to do something based upon inferred feedback. Oh yeah, that was good because somebody clicked on things or not. And then you need to start worrying about reinforcement, and you need to start worrying about biasing effects and so forth. Another area that you might want to think about is one-shot learning. In one-shot learning, typically what happens is you have about one example to learn from, and then you need to do well given that one example. So if you take a look at our existing learning algorithms, they typically work pretty poorly when you have about one example. When you look at what one-shot learning systems are doing, they're typically using the actual training example. The training example is there, which is very different from the way that that our other supervised learning algorithms work. Our other supervised learning algorithms use the training examples to produce a model which does not contain the training example anymore. Another thing that you might want to worry about is true conversational systems. If you want to talk to a person, they have a vast amount of experience over their lifetime they can leverage into that conversation. And that's just very different from what existing learning algorithms today can do. And existing conversational systems kind of parlor trick this, but they're not very effective. This gives you a sense of applications where it's easy to imagine that having a contextual memory system would be very helpful and effective. So let's think about a little bit about what would be needed. First of all, right, so in existing learning systems, oh, I should say, if you have questions, you should ask. In existing machine learning systems, what typically happens is there's some sort of gradient descent going on, and all of the examples that are going into the system are erased. Now, it's not true for some things like support vector machines or nearest neighbors, but those tend to be computationally intractable. And so they are not used so much. They also have some representational difficulties in some situations. The strange thing is that people have been experimenting with memory, right? So there's like the differential neural computer or whatever. The memory that they're using is incredibly small, maybe 1,000 cells. And the reason why it's incredibly small is because they have to do differentiable things over it, which means that all their operations are linear in the number of cells, which is not a great state to be in. So in contrast, computers are great at memory. Humans are not that great at memory for short-term memory, but they're actually over a person's lifetime, they can accumulate a vast amount of experience they can pull on for solving problems, and that matters. So how do we make a learning algorithm that can work with a large memory effectively? Right? So that's kind of the question. And this is one of the things which, so I think we're kind of in the differentiable paradigm for learning nowadays, and you have to actually move a bit beyond the differentiable paradigm if you want to succeed here, because you cannot afford to compute gradients over 10 million things or a billion things or whatever. That's going to be, in order to do an update, that would be ridiculous. Okay, so let's start with what is a good memory. So we need to think about what are the desirable criterias for what a good memory controller would be that can interoperate with the learning algorithm. And we're just going to focus really on what that memory controller looks like and how it might be used a little bit. All right, so we want the computational time to be fast. This is one of the primary things. We cannot afford to have, so one thing that you could imagine is, suppose you're going to try to build a face recognizer for Earth, right? So 6-7 billion people. You could imagine doing a 6 or 7 billion size computation for every single recognition that you want to do, but that would be ridiculous, right? Instead, you want something which is going to be very different from that. And as a goal, I'm saying we want something that's logarithmic in the number of memories. Okay, so then another issue that can come up is, okay, so whenever you're trying to do things fast, you can often do things faster by using ancillary memory of one sort or another, right? You can have many different lookup tables, and those lookup tables can end up taking much more space than the actual objects themselves. And that's undesirable, because we're thinking about a situation where we have a large number of memories by definition, and so having a large overhead and a large number of memories would not work very well. So we'd much rather have a small overhead on a large number of memories. So we want to have the overhead be sort of a constant scale or less per memory. Self-consistency is an important one. So we're thinking about an associative memory, where you put in a current context and out comes the memory. And if it happens to be the case that the current context is equal to the memory, then the memory should really come up. That's kind of a definition of what a memory is in some sense. One more here is incrementality. So this is, I think, really related to the computational desirability of a system. So you want a system where you can add memories over time without overly disturbing the system, or without needing to relearn the entire thing all at once. Right? And then the last one is that you want something that learns. Right? So you want a system that learns to return the right memories. And I think an example of this is my wedding. Right? So when I got married, we were at a restaurant, and the exact details of you know, how people were seated, or you know, what was served and whatnot, that's not very important as memories go. The fact that I got married, that was actually the important thing, right? Nevertheless, I can recall the other things, but I'm not recalling based upon the seating arrangement. I'm recalling based upon getting married, right? So you want a system that can learn to recall the right things, the things which are most relevant to a given situation. And so we want a system that can actually learn to return the right memories. All right, so these are our criteria. And given these criteria, we can think about an interface which kind of exercises the system. So this is not an algorithm, this is just kind of what you can do with the system spelled out as if it was an algorithm. So in an online fashion, we're going to observe queries, we're going to return results. The number of results that we return should not be too large. It should be at most logarithmic in the number of memories, because we're trying to achieve logarithmic time. We can observe feedback. You know, that was for this query, that was a good memory, or that was a bad memory. And then we can also insert new memories into the system. So these are the kinds of interfaces that we want to support. So we're in the extreme multi-class workshop, and maybe it's worthwhile to think about what this means as kind of extreme multi-class. So think of every example as being its own class to get a sense of what we're trying to do here. And in fact, the algorithm that I'll show you in a moment is quite related to an algorithm that we published this year at ICML for extreme multi-class. Okay, so let's think about other approaches, other ways we might try to solve this problem. And if we look at them with respect to our criteria, we'll see that they're all a little bit lacking. So the simplest one is a hash map, right? Every programmer knows this, every programmer uses this more or less. Hash maps are great. Compute-wise, storage-wise, and self-consistency-wise, they're even incremental, but they don't do learning. And so they don't really learn to use context to retrieve the right memory in any kind of effective fashion. Instead, you have to have exactly the right context, or else it doesn't work. You can do inverted indices. This is very common in search engines. Compute-wise, they can be good. It's not always the case, but they can be. Storage-wise, they can be good. Self-consistency, they can be good. They're typically not at all incremental. It's modifying an inverted index to where it operates in an incremental fashion is not so easy, and then they don't really learn that well. In fact, at all for most of them. You can do nearest neighbor. So nearest neighbor is terrible compute-wise. It's great for storage, self-consistency, incrementality, and then in terms of learning, it doesn't actually learn typically. You can, of course, try to learn a metric, but then you lose incrementality. So it's sort of you lose one or the other. You can do approximate nearest neighbor. Approximate nearest neighbor is like a LSH, locality sensitive hashing. So it's good in the compute paradigm, but it doesn't really support incrementality and doesn't really support learning in an effective fashion. You can do a learned hash function. So that's typically not adequate compute-wise. You can try to combine it with other algorithms for searching over a large space, and sometimes that works, but it's a little shaky. You can do, all right, so you typically lose badly in incrementality, but you do get learning, right? So you're actually learning the hash function, and that ends up being very powerful sometimes, right? So if you didn't care about incrementality, and you had sometimes it's the case that you can actually search effectively over the set of hashes of things, then that could work. You can think about differentiable memory. Differentiable memory, ooh, what's wrong? This should be yes here. It is learning, definitely. But it doesn't really deal with incrementality effectively. You can't insert new memories at a large scale, and it doesn't really deal with the compute effectively because the time is typically linear in the number of memories that you're working with. The last category is supervised learning in general, not including any of the above. Compute varies, incrementality varies, self-consistency typically does not exist because the actual memories, the actual observations that you want to store are not a part of the model. All right, so that's other approaches, and this is about where we are. We have something that satisfies all of the criteria except for self-consistency, and even that is satisfied mostly. Okay, so I'm going to tell you essentially a data structure. And so I want to start by just telling you what the data structure is and then how you operate on the data structure. And then we'll discuss a little bit about the experimental results. There's not too much yet, but there's something. Okay, so we're going to think about a tree-like data structure, which has internal nodes and leaf nodes. An internal node is going to have a left child and a right child. And it's going to have some predictor, G, which is going to be used to route on that internal node in the future. And then we'll have a count of the number of things beneath that, number of memories beneath that internal node. We'll also have leaf nodes, which have a collection of points, which aren't too large. It's only going to be logarithmic in the number of points overall. And then we'll have a count of the number of things in that leaf node. All right, so then a tree is going to consist of a root node, and then we'll have a balance parameter, which we'll use to control how deep we allow the structure to become, or rather, how imbalanced we allow the structure to become. So this is the basic data structure. Are there questions about this? Actually, are there questions about anything so far? Let's think about querying. Querying is the most simple operation you could hope to do. querying is about as you would expect. We're going to use the root node, and then while we're not at a leaf, we're going to use the G function in each node to route to the right or to the left. And then once we reach the leaf, we'll have a set of points, not too large, logarithmic in scale, and we're going to just choose the most relevant memory amongst that pool. Right, so then update is the next thing we might think about. So we've returned a memory, and now that memory has some value. And I'm just going to show it here for a single element. Right, so we queried on x, returned xi, and that had some value ri. We're going to run down the tree, all right, so now we get to the tricky bit. So it's important to understand that G here is not a classifier. It might appear to be a classifier because it is making classifications, just choosing right or left, right? But G is not actually truly a classifier because it's really a partitioner. It's something which is routing some things to the right and some things to the left. And you'll be unhappy if everything goes to the right. You'll be perfectly fine if the definition of left and right swap uniformly for everything, right? So that's not true of a classifier in general. So this is a partitioner. Now we want to have a rule for creating that partitioner, which is going to work in an online fashion and enforce some sort of logarithmic depth constraint, right? So we're going to do that. This is what we're doing at the moment. You have your existing prediction about whether or not you should go right or left. And then you have the number of things to the right and the number of things to the left. So if you take 1 minus alpha of the first plus alpha times the log of the second, you can create a label which, if you optimize against it, will enforce logarithmic depth. Right? And then the question is, of course, what label do you want to use? I think typically which alpha do you want to use? And I think typically we're using about 0.1. Okay, so then we create this label, we do an update on that router, and then we just route according to whatever the prediction is. So in particular, the prediction may not be the same as what the label says, and you want to go according to the prediction because it's important that you only update at lower nodes if it's actually relevant to what you're trying to learn or what you're trying to update. Okay, so then at the bottom, you want to use an update on the f function, right? So once you reach the leaf, you can just pull up the individual xi and make the update. Right. So then another operation we want to support is insert. Insert is very similar. What? Interesting. I don't know where that came from, but okay. So we're running down through the tree again. We have this balanced based label. We can do an update. We want to keep in account of how many samples there are at a node. We want to route, and then we want to add the memory at the leaf. Okay, so this alone would not be adequate because if you think about starting with a leaf, you just end up pulling everything at the leaf at the root. So you also need to be able to split a leaf. So once the number of samples at a leaf grows too large, you want to do a split. Right, so how do we do that? Well, we're going to make V an internal node. We create new leaf nodes left and right. And then for each x in the different points, we're going to insert that x. Here what's happening is we're allowing you to give feedback about existing memories without necessarily inserting a new memory. Right? If you want to insert with some sort of relevance, because I don't know what the semantics of that relevance would be. Right? Because you need relevance is with respect to something. It's with respect to some query. So if you just do what I told you so far, you don't get self-consistency. You get self-consistency for the one insertion that you just did, but they may violate self-consistency for many previous insertions. And so what you want to do is essentially experience replay on the insertion process. So what you can do is you can run down through the tree structure, removing some random point, and then you can reinsert it. And now if you have an online update rule, which is thank you, which is no regret, meaning it will eventually converge to a solution which is near the optimal. Then this actually gives you self-consistency. Okay, so let me give you an example of applying this approach. We're going to do ImageNet 20K, but with 3-shot learning. So we have 3 training examples and 1 test example, and there are 20,000 classes, right? So it's 3 training examples per class. Just be clear about that. Okay, so at ICML, we published a paper called the recall tree, which is actually using some similar approaches to learning. It's different in several details, but it's a similar style where you have some sort of tree that you're building. And you can ask, okay, so we're trying to do something very hard. We're trying to predict which of 20,000 classes is the correct class with 3 training examples, right? So if I just tell you error rates, it's going to look like, oh, terrible, 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 and terrible. But we can be a little bit more refined in how we look at things. Instead, we can say, at 1 in 20,000 random guessing, you'd have some performance. The recall tree gives you better performance than 1 in 20,000. How much does the entropy get reduced by going through the recall tree? So what is how many bits have you effectively added to the system? And the answer ends up being about 3 bits. So you've reduced from random guessing by about 3 bits. Right? And then you can say, oh, there's an older algorithm called the filter tree that we worked on, and it happens to work better here. It's kind of interesting to ask why. The recall tree is actually learning the structure of the partitioner, like what I'm showing you now. The filter tree actually has a predefined partition over the class labels. So again, both the recall tree and the filter tree are using the class label directly in the learning process in a way which the memory does not use. Instead, what's happening with the memory is just we're going to pull up a memory and we're just going to use that label as if it was our prediction, right? So these are both logarithmic time approaches, which are using the label information at training time in a stronger sense than you can use with a memory controller. Okay, so let's keep going. You can also do a one against all approach, right? So you can say, look, I have 60,000 examples, 3 from each class, and I can just build a predictor of, is this the best class or not for each individual class. And then you can take an argmax and make a prediction. This would be terrible computationally, but you know, it's only 60,000 examples, and it's only 20,000 test examples. You can afford to do it. So you can brute force this, and that actually works a little bit better. Sort of amazing that you can learn given only 3 examples, but there's actually a substantial entropy reduction. I think we're up to about 4 bits right now. And then you can do the memory tree, and that puts you up to about 6 bits. So something is going right there in terms of being able to work with a very small amount of information to learn. And if I had to say what it was, then I think that the routers are letting you narrow in on things pretty effectively. And then you have that pool of examples and that comparator which is going on at the bottom. And because you can pull up individual memories rather than having all of your examples embedded into your parameters, you can get substantially better performance. So right now in the update, we're using the reward, but in the routers, it's turned out to be tricky. I think it does make sense, but the right way to do that, which actually improves your performance, is not clear to me yet. Yeah, so I actually misspoke. When I said bits, I actually meant nats, by the way. So the memory tree, this is actually about a 97% error rate. So the obvious upper bound you could get to is 0% error rate, right? In which case you'd be looking at the natural log of 20,000. Right, so you can compute what that is. It will be a bit higher, but not dramatically higher on this scale. That may be correct. We may not be able to expect to get that, but we can certainly try. I think it's an ideal to strive for. So this is, it's available. It's one that was been used previously in the, I think a recall tree paper. So this was a convolutional neural network in which we scraped off to get the top layer. So the layer before the top, actually. And that's what the features that are being fed in to the system. Yeah? The prediction accuracy of what? Prediction accuracy of g of x. Yeah. I don't know yet. Yeah. 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 So what I can tell you is that after you do this experience replay type thing, it's slightly more complex than that because you need to remove and then add the point again. But after you do that, the fraction of points which are reaching, which are self-referential, which are self-consistent, is well above 90%.